Welcome to my YouTube channel.
In this video, we will take a look at linear homogeneous systems. Dynamical equations are of the form x dot equals ax plus by and y dot is equal to cx plus dy. This is a 2 by 2 dynamical system. Dynamical system. So this is the form in which it is given by. And we have the first way to solve it. We have the characteristic. Equation. And the second way to solve it, we have the determinant and trace approach. So we have these two approaches, concluding on the behavior of our system. The first one is the characteristic equation, and the second one is the determinant and trace approach. Remember, this is for 2 by 2 dynamical systems. It doesn't work for 3 by 3, it doesn't work for 4 by 4. So we can determine the behavior of our 2 by 2 dynamical system using these two methods. Now, the first method is quite easy because at the end we would have our characteristic equation to be lambda squared minus the trace of A, if we have A as our matrix, times lambda plus the determinant of A is equal to our polynomial. This is a polynomial equation. So if our polynomial equation is equal to 0, then we can find the value of lambda using this equation. So the trace of A lambda plus the determinant. So remember, this is your thesis. So if this is equal to 0, then this will be equal to 0. And this is true. Okay, so we will use this method. Now, since you're using the determinant and trace approach, it implies that we're going to conclude on the behavior of our system using the determinant and the trace. Now, these are the following. If the determinant is less than 0, we have a saddle. If the determinant is greater than 0 and the trace is also greater than 0, then we either have a node, which is either stable or unstable. If our determinant is greater than 0 and our trace is less than 0, then we have a focus, which is also either stable or unstable. If we have our determinants to be greater than 0 and we have our trace to be equal to 0, then we have a center. And lastly, if we have our determinants to be equal to 0, we cannot conclude. So inconclusive. Now you might want to ask, why is it that when the determinant is equal to 0, we cannot conclude? And I'll show you that in a bit. Now, when we look for the values of lambda, we are actually calculating for the eigen values. And from the eigenvalues, we can find our eigen vectors. So our lambda is what will allow us to find our eigenvectors. Is that okay? So our eigenvalues helps us to find our eigenvectors, and every eigenvalue has a corresponding eigenvector. So for every eigenvalue, you can find a specific eigenvector for it. Now, when you trying to find the eigenvalue using the determinant and trace approach, we use this formula, which is tau plus or minus the square root of tau squared minus 4 delta, all divided by 2. I said this, that when you have your delta to be 0, we cannot conclude on the behavior of the system. Now, look here. If delta is 0, and let's assume delta is 0, so we have our lambda to be equals to tau plus or minus square root of tau squared, because delta is 0, so this whole thing is 0, divided by 2, which would then give us tau plus or minus tau by 2. And we're going to have one of our eigenvalues. We're going to have tau plus tau divided by 2 will give us tau. We have 2 tau divided by 2 will give us tau. This is for the first one. And for the second one, we'll have tau minus tau divided by 2 will give us 0. Now, when the eigenvalue is 0 for linear systems, we cannot conclude. Is that okay? I cannot make any conclusion based on any eigenvalue equals to 0 for linear systems. That's why I said when your delta is equal to 0, we have what an inconclusive analysis for linear systems. Okay. So we are going to use this same approach to solve an example. We are going to find the eigenvalues. We're going to find the eigenvectors. So let's take an example. Let's say we have our system x dot and y dot to be 3x plus y, and y dot to be x plus 3y. In this way, we will write down our matrix. So let's A be equal to, the first column will be this value and the value here, which is 1. So we have 3, 1. The second column, we have 1, 3. Now, we are supposed to find our eigenvalues and eigenvectors. So we're going to find our delta. It is given by the determinant. We multiply 3 by 3 minus 1 by 1. So 3 by 3 minus 1 by 1. This will give us 9 minus 1 will give us 8, and 8 is greater than 0. For our trace, we add the elements on the diagonal. Is that okay? So for our trace, we'll add the elements on the diagonal. We have 3 plus 3, which is equal to 6. Is that okay? And this is also greater than 0. So this means that the system is a node. Is that okay? We're going to look at which type of node, whether it is a stable node or an unstable node. And we can come to this conclusion using this formula. Lambda equals tau plus or minus the square root of tau squared, and it's 4 delta all over 2. we have lambda is equal to, we have tau to be 6 plus or minus square root of 6 squared is 36 minus 4 times 8 will give us 32, 4 divided by 2. So I can write 3. I hope you get me. 6 divided by 2, we have 3 plus or minus the square root of 36 minus 32 divided by 2. So this will give us square root of 4, and square root of 4 is 2. This is what I'm saying. We have 3 plus or minus square root of 4 divided by 2. And this will give us 2. This will cancel this 2. It will give us 1. So we have lambda equals 3 plus or minus 1. Okay. So our lambda 1 will be 3 plus 1 is equal to 4. Lambda 2 will be 3 minus 1, which will be 2. So in all, our lambda 1 is equal to 4, or lambda 2 is equal to 2. Now, for this, each of the lambdas, we are going to find the corresponding eigenvalues. So you're going to use this formula for finding them. E minus lambda I times V is equal to 0. Is a vector. Is okay. Since we are using the first lambda, you're going to have E minus lambda 1I V1 is equal to 0. Now, E is given by 3, 1, 1, 3. So we have 3, 1, 1, 3 minus our lambda, we have 4. Lambda 1, we have 4. Remember, this is the identity matrix. 4 multiplied by x and y is equal to our 0 vector. So we have in all 3 minus 4 will give us minus 1. 1 plus 0, which is 1. And 1. And then 3 minus 4 again, minus 1. Times x and y is equal to our 0 vector. Now we just need the first part. Is that okay? Matrix multiplication. So whenever you have a matrix, you know how to multiply a 2 by 2 matrix. So we have minus x plus y equals 0. Is that okay? So we have x is equal to minus x is equal to minus y. Multiply that x is equal to y. Now, if x is equal to y, we divide y by x. So y divided by x, you have 1 over 1. So if y is equal to 1, x will be equal to 1. So our first vector, which is v1, we have 1, 1. Now our next eigenvalue, we have lambda 2 to be equal to 2. So a minus lambda 2I v is equal to 0 vector. And this is given by, we have 3 minus 2. We have 1 here. We have 1 here. We have 3 minus 2. We have x and y are 0 vector. And now we are going to have 1, 1, 1, 1, x and y, 0, 0. Well, matrix multiplication. This times this. So x plus y is equal to 0. And from here, we know that our y is equal to minus x. And if you do our y divided by x, you're going to have minus 1 over 1. So if y is equal to minus 1, x is equal to 1. So our v2 will be equal to 1 minus 1. You know what I mean? So we are going to write down a matrix which is made up of the eigenvectors. And this is invertible matrix. It is made up of V1, V2. So the matrix, before you can find the determinant, you have to make sure that the matrix is invertible. Is that okay? That means we can find the inverse of P. And we can find the inverse of P easily using the one over determinant. The rows adjoint. One is a 2 by 2 matrix. We just use the normal equation. If we have A, B, C, D, the inverse of A is 1 over the determinant times D A minus B minus C. So that's what we're actually going to use. So we'll have to have minus 1, minus 1, minus 1, and 1. So P inverse will be equal to 1 over 2, 1 over 2, 1 over 2, minus 1 over 2. And we know that when you multiply P inverse, you're going to get the identity matrix, which is 1, 0, 0, 1. So P inverse, we have 1, 1, 1 minus 1. We have 1 over 2, 1 over 2, 1 over 2 minus 1 over 2. Which is going to give us 1 over 2 plus 1 over 2. And 1 over 2 minus 1 over 2. 1 over 2 minus 1 over 2. 1 over 2 plus 1 over 2. And half plus half, we have 1. We have 0. We have 0. We have 1. So this is true. So in the end, we found that our matrix is invertible. Is that okay? We're able to confirm that the P inverse was able to give us our identity. Now, in our next video, we will look at the phase portrait and how to construct them. Thank you, and see you in the next video.